Good morning to all of you. Today I will start with the fifth chapter in your syllabus. So I want to make the syllabus of sessional 2 clear. The syllabus for sessional 2 is chapter number 2 of your syllabus, right? What we have already covered regarding the random processes, and chapter number 5. Chapter number 2 and chapter number 5 will be in your syllabus. So that I will be starting today, which basically deals with Gaussian noise as a random process. And we will discuss about the Gaussian distribution and Gaussian random process, right? So this thing is very clear that syllabus for evaluation 2 is chapter number 2 and chapter number 5 of the syllabus. And chapter number 3 and 4 will be in your offline classes, right? For which the written test will be held. All right. I will put these things on LMS also regarding your syllabus of evaluation 2, which is of 10 marks question, objective assessment. Anyways, let's now start with the chapter number 5, right? And which basically I will start with the Gaussian distribution. Central limit theorem we have already discussed actually, but I will again just a kind of reference to explain Gaussian distribution. I will refer to central limit theorem also, and then I will discuss Gaussian noise. After this, I will share a second PPT in which I will discuss about the autocorrelation, the power spectral density of noise. And then I will discuss what is white noise. And at the last, I will discuss Gaussian random process. All right. So let us now start with what is Gaussian distribution, first of all. Very important distribution. This is also known as normal distribution, right? We will talk more about the Gaussian distribution also in the after when you will have your offline classes regarding the hypothesis testing and the p-values and the z-score also. But let us start with the Gaussian distribution. Now, this is the graph of the Gaussian distribution. Let us say I have a random variable capital X, right? And along x-axis are the values of this random variable values of this random variable x, which are represented on x-axis by small x. Along the y-axis is the probability density function, and this is the graph. So this graph is a bell-shaped curve. It goes towards the minus infinity side, and it has x has got both the values, positive and negative. Right, this mu is actually the mean of this distribution. All right, and there will be one more parameter which will be sigma. Sigma is the standard deviation, which tells us about the width of this bell-shaped curve or normal distribution. Width of this probability distribution. Mu and sigma are two parameters which can control the shape of the distribution. All right. And the distribution is given by probably the PDF P subscript X of X. It is given by 1 over under root 2 pi sigma square exponent of minus x minus mu whole square divided by 2 sigma square. So this is the normal, this is the probability density function for a Gaussian distribution for this random variable capital X. Now, if you look at this is a bell-shaped curve because the probability density function looks like the shape of the cross-section of a bell. This looks like the cross-section of a bell. So that's why this is known as, very popularly known as bell-shaped curve. Now, this equation is the equation for the probability density function. So we will take this equation. Please, keep this equation in your mind for Gaussian distribution, and keep this graph also in your mind, that this is the graph, but it takes on negative values also along x-axis, and it takes on positive values along x-axis. Mu is the mean of this curve, and sigma will give me the width of this or the variance or standard deviation of this bell-shaped curve. Now, equation 1 is the equation of the probability density function. Mu and sigma are variables, and it turns out that mu is the mean of the PDF, and sigma is the standard deviation, or sigma square is the variance of this random variable, and sigma indicates the width of the curve. Sigma indicates the width of the curve. Mu and sigma are two parameters which change the shape of the curve. We can control by changing mu and sigma, we can either make this curve thinner or broader. So mu and sigma will be two parameters which can control the shape of the curve. All right. Then the question is that why Gaussian distribution is so famous. Now, if you know regarding your mark system in Thapar, you get marks, but it is generally said that the marks distribution in a class is Gaussian, has to be Gaussian, right? It has to take a Gaussian bell-shaped curve. Now, but that is a very loose way of representing the Gaussian distribution. If you look at this distribution, this function is a continuous function, first of all, but marks are not a continuous function, rather they are discrete values. Marks of students in a class, that is marks of students, are scaled according to the bell-shaped curve, according to Gaussian distribution. Students tend to get marks in a class distributed. If you plot histograms of their marks, you will observe that some will tend to get lower marks, some will tend to get higher marks, and maximum will be around mean. But that's what I'm trying to say, that Gaussian distribution is not exact function to use in this case, because the marks are, discrete value, but we use it, right? But this is not a correct way of using the Gaussian distribution, because as it is written here, this function is continuous and marks are discrete. The random variable, which is marks, is a discrete random variable. And in the graph, you know that this graph goes from minus infinity to plus infinity. So this is not a well-suited distribution for marks, right? Now, the question is that, so why is that Gaussian distribution is used then? It is used in many explanations, many types of data, right? Now, to answer this question, why it is so famous, to answer this question, we have to once again look at the central. Please mute your microphone. It leads to what we have to look for is the central limit theorem. If you remember, I talked about the central limit theorem, but let us look at the central limit theorem in the context of the Gaussian. Request you please mute your microphones. So central limit theorem says that any number of random variables, if they have the same type of distribution, and if you add them up, that's what central limit theorem. I will formally define the central limit theorem here also. This theorem says that if you have any number of random variables and they have the same distribution. Astic Saluja. Okay, I have muted. So central limit theorem. This is that any number of random variables, if they have the same distribution, and if you add them up, then the overall distribution will be a Gaussian distribution. If you remember, while I was trying to explain you the central limit theorem, whatever the type of distribution the random variables have, let us say that they don't have Gaussian individually, they don't have Gaussian distribution. Whatever the type of distribution the random variables will have. But if you sum these random variables up, and as the number of random variables, as n approaches to infinity, the joint, the collective distribution, the overall distribution will turn out to be a normal distribution or Gaussian distribution. That's what the central limit theorem is. And I proved that. If you look into the notes, you will see that I have proved that also, that it looks like a Gaussian distribution. That's what I'm trying to explain here. If you have two random variables, n plus m, so these need to be added. Let's say, I will come back to the noise part. Because if you look at the Brownian motion of electrons, electrons having the Brownian motion, it's not Gaussian, but it's not Gaussian distribution. But if you collectively add all the random variables which we are using to represent the movement of the electrons, then if you add all the Gaussian random variables, then you will see that the overall distribution, that the individual probability distribution attached to these random variables, the overall distribution will turn out to be a normal or Gaussian distribution. That's the power of this central, very powerful theorem. This is central limit theorem. So the question is that they all add up to Gaussian distribution. So that is why the Gaussian distribution is so important, that in many cases, that if you try to model a complete system, it turns out that the overall probability distribution is a Gaussian distribution. Right. Then this is the central limit theorem. We have already done this. Let's say these are the random variables. If all random variables are taken from the same distribution, if these are independent, if they have the same mu and sigma squared, then this is, let's say, y, which is the summation of all the random variables. And this is subtracted from the mean, or add all minus their mean, divide by the square root of the number. Then you get a new random variable. This is your new random variable y. And central limit theorem states that under weak conditions, the probability distribution function of y is Gaussian. It is not necessary that the probability distribution of this xk is Gaussian. It may be any distribution, but we are taking the random variables from the same distribution, having same mu and sigma square. They are independent, but if you will add them up, and let's call this random variable as a y, right? So probability distribution of y is Gaussian as n tends to infinity with mean 0 and variance sigma square. Right? So that's the power of the central limit theorem. And I have just explained what is Gaussian distribution. I have talked about where the Gaussian distribution, how Gaussian distribution is helpful. Even if the random variables don't have, but when you sum up all the random variables, it will turn out to be Gaussian distribution, which the central limit very powerfully states. Okay, so let's now talk about what is Gaussian noise, because our main goal is Gaussian noise. To explain this, I will talk this Gaussian noise in terms of a communication system, the model of a communication system. Very simple model I will try to explain, because this is not a digital communication subject, but I will try to explain you in a very simple way a communication system and from where the noise is coming. And what is that noise? Let us say in a digital communication system, I want to transmit 0 and 1, 0 or 1 at one particular point of time. At one particular time period, I want to send either 0 or 1. Very crudely, let's say I represent 1 with 5 volts and 0 with 0 volts, right? So I am sending these pulses to represent 1s and 0s. Now these pulses will pass through the channel. Whatever the channel may be, anything. It can be a wired channel, wireless channel, any C channel, water, so any type of channel can be there. Right, so these 1s and 0s are passed through the channel in the form of these pulses. And when it passes through the channel, it is received at the receiver. Because at the receiver, the signal will be very weak. What we will do, what we used to do is that we amplify the signal. And then with this integrated, don't worry about what is this integrated. We are only doing the average. within that sample period for which this waveform is there. If we are integrating whatever the amplitude is coming, whatever the signal is coming, we are integrating from 0 to capital T. This is basically giving me the average value. And then we are sampling the average at every T time. All right. This is averaging, this is sampling. So when the signal is passing through the channel conditions will attenuate the signal. All right. So the complete receiver needs, first of all, the channel will attenuate the signal. Right. If we, let us say, transmit XK signal to represent 0 and 1, if we transmit XK signal and we receive YK signal, channel will introduce some kind of attenuation. Right. If it is, don't worry about what that attenuation is. You can very well intuitively find out that whenever a signal is transmitted from, let's say, this end to, let's say, Delhi, or to some, let's say, 10 meter, 20 meter, 30 meter, 1 kilometer, the signal will, as the distance goes on, the signal power will fall. And actually, it falls with the square of the frequency. Let's not go again into those details. The point is that the signal power will fall. So that means the signal is attenuating. Channel is attenuating the signal. That's why we are amplifying it and integrating it, then sampling it, and then we are getting the sampled version of the received signal, which is YK. Now the question is that the receiver will be, how the receiver will be implemented. The receiver will be implemented using electronics. There will be amplifier, there will be some DSP processor, there will be some microprocessor, microcontrollers, other associated electronics will be there. So all this will be made up of electronics. Right? So that's what I'm trying to explain here. Let us say H is the attenuation during the channel transmission, and YK is the signal received. So XK was the signal transmitted. YK will be equal to H into XK because H is the attenuation. But the point that I want to stress upon is that the receiver is made up of electronics. The complete receiver needs electronics and needs to turn on a power supply, right? You need to turn on the power supply to power these amplifiers, the process, all the electronic circuitry, right? And when we are using the power supply, the electronics present in the receiver will heat up. And due to the heat, the electrons will start moving due to the heat in various parts. Right. So once the electrons will start moving due to heat, due to the power supply given to the electronics, and we call that as noise, the internal noise of the circuit. And at various points of the circuit, amplifier or resistances, capacitors, at every point of the circuit, the noise present at different times is a kind of a random variable. Amplifier, one random variable. Very crudely speaking, amplifier one representing one random variable. Resistor representing another random variable. At different points of the circuit, various random variables. Right? The question is that's what the central limit theorem is coming into picture. As I said, when you add up the distribution of these random variables, right? That will result into the overall distribution will be a Gaussian distribution. And that is why we say that we can model the noise present in the electronic circuit, which here in this example, I'm considering a receiver, and we can say that the noise is actually Gaussian. I'm using the word only at present, I'm using Gaussian noise. It should be very clear from where the Gaussian noise has come, right? Electron, I have written down everything so that you can clearly understand. We don't simply receive H, we don't simply receive the attenuated version of the signal xk, rather we receive noise also. So therefore, this is the model, this is the equation which we will receive. Yk will be equal to h of xk. H is the attenuation, xk is the transmitted signal plus noise signal. Sampled version of the noise, because we are putting here a sampler also. Noise is also sampled. And we call this noise as additive white Gaussian noise. Gaussian noise I have already explained, right? Additive means this noise turns out to be adding into the signal in a normal addition process. It is additive. Noise is adding to the signal in a normal additive fashion. So that is why, forget about this white at present. That is why the word additive is there. The Gaussian noise. I will come to this white part just a little bit on. Okay. So this is about Gaussian noise. So if you plot Yk, what is Yk? Yk is the sampled version of the noise. And if you plot this Yk, the samples of the Yk, along x-axis are the samples, the n. The samples, first sample, third sample, fourth sample. If you plot all the samples of the noise, you will see that the overall distribution of the noise samples will turn out to be Gaussian distribution. If you plot Yk and do many measurements, it will turn out to be Gaussian distribution. And we are assuming here the noise samples for different k are independent of each other. Noise is independent and identically distributed. Identically distributed means the noise samples are coming from the same type of distribution. So that's the assumption that we are making: identically independent and identically distributed noise samples. So at any identically and independent, so noise samples at this point or at this point, no 2 points of the noise samples are correlated to each other. At any pair of times, the values are identically distributed and statistically independent. So therefore, we can very easily say that the noise samples are uncorrelated. That's very important factor we need to keep in mind. The noise samples are uncorrelated. What are noise samples? I have already explained from where the noise is coming. This is not through the channel. Through the channel, it is attenuation. I am talking about the noise which is coming from the receiver electronics. And then since we are doing the sampling of the signal also, the noise also gets sampled. Once the noise also gets sampled and we try to plot the values of the noise with respect to the sample number, then it turns out to be a Gaussian distribution. And we are assuming that the noise samples are independent and identically distributed. So if they are independent and identically distributed, no 2 samples are related to each other. They are uncorrelated. That's what is said here. Hence, the noise samples are uncorrelated. Is that clear? So I will just actually stop sharing this presentation. I will share the next one. Okay. Sorry. Share this same thing. I hope this is clear. This presentation is visible to you, the new presentation. Right. So this is related to the autocorrelation, the power spectral density of noise and white noise. Let us try to understand, to find out the autocorrelation function of noise, the power spectral density of noise, and let's see what is white noise. Because in the previous presentation, in the previous slide, you came across with the term AWGN. Gn is clear, which is Gaussian noise. Additive is because the noise is being added to the signal in an additive linear addition way, linear addition way. And now the point that I want to explain is the white, the meaning of the word white, why it is called AWGN noise. So let's look at, first let us start with the autocorrelation function. Since we have already done the statistical and the probability concept, so we know what is autocorrelation function in random processes. What is the autocorrelation function? At two different of the same process at two different times. This is given by the expected value of the xt1, xt2. Here it is the conjugate, right? So autocorrelation is the expected value of multiplication of two random variables taken from same random process x, one at time t1 and other at time t2. And we also know that what is a wide sense stationary process. In a wide sense stationary process, the individual timings do not matter. This is the case of strictly stationary stochastic process. But if it is wide sense stationary process, then the individual times do not matter. Rather, the autocorrelation function will basically depend on the difference between the times in a wide sense stationary process. So autocorrelation function, I can, if time difference between T1 and T2 is denoted by, let's say, tau. So Rx tau is given by x of t into x conjugate t plus tau. The difference between the time matters. And mean and variance do not vary with time. Absolute value of x for T1 does not matter. It is same for all. Absolute value does not matter. Rather, the difference between the timing. If we are able to prove that the autocorrelation function depends on the difference between the time, is a function of difference between the time, two different times, then we will say that it is a wide sense stationary process. Okay, so let us try to understand the autocorrelation function. This is the autocorrelation function. I have equation I have put xt into x star, forget about, don't worry about this x conjugate t plus tau. Now when tau is 0, when tau, okay, first of all, let us also at the same time, okay, I started with the autocorrelation function. So this is the autocorrelation function. And in a wide sense stationary process, the autocorrelation function is dependent on the difference between the time. So we can write the autocorrelation function to be expected value of xt into x star t plus tau. Tau is the difference between the two times. I will at the same time now define what is power spectral density. Power spectral density is, let's say, denoted by Sx. X is the S is the power spectral density. X is the subscript, which basically represents the random process, right? Or a random, and F is the in terms of the frequency. This is the Fourier power spectral density will be in terms of the Fourier analysis. So it will be in terms of, we have to actually take the Fourier transform of the autocorrelation function. It will give you the power spectral density with an argument of frequency, right? We know what is autocorrelation function. Once we take the Fourier transform of the autocorrelation function, this is basically the power spectral density of the random variable, right? Now let us say that, let's take the case of a digital communication system again. When we are transmitting 1, we represent it with plus a. When we are transmitting 0, let's say I represent it with minus a. T0 is the time offset between transmitter and receiver. Time offset means when you are sending the signal from transmitter and it is reaching to the receiver. Let's say T0 is the delay between the transmitter and receiver. And we can say that T0 is a random variable, is a random process basically. Because there will be different times for different receivers and T0s are random. Heights or even the heights of A1 and 0 are random, because if the channel conditions are bad, the height of A will be different. If the channel conditions are good, the height of A will be different. But only constant thing is that capital T, which is the sample period. So this is not random. T0 is also random, and the amplitudes A or A minus are also random. Capital T is not random. All right, so now let us look at the autocorrelation function. So autocorrelation function, when tau is 0, autocorrelation function is given by the expected value of xt, x star t, because tau is 0. So when along x-axis is tau, when tau is 0, the autocorrelation function, so xt can be either a or minus a, ultimately it will give me a square. So when tau is 0, it will be a square. But when it will be a square, right? When tau is 0. So for values of tau not equal to 0, let's take two cases when tau is greater than t. So when tau is greater than the time period, then you will always be in different digital time slot, no matter what T0 is. T0 is the time difference between the transmitter and receiver. When your difference, or when you are taking the autocorrelation function, tau, the difference of the time is greater than the time period when you have to sample. All right. No matter, each data bit is independent, especially in data compression, equally likely of chance 1 and 2. Half the time it will remain a square, half the time it will remain minus a square. Right. So the expected value, it will be 0. When tau is greater than t. So when tau is, that's why when tau is greater than t, the expected value, the autocorrelation function will be 0. But when tau is less than t, so autocorrelation function value will approach to a square for tau equal to 0. So when going from minus t towards tau equal to 0, it will take a it will take a ramp kind of triangular kind of function. So autocorrelation is basically a triangular function. So there may be chance of transition between t. Sometimes there is no transition, will depend on the value. Nothing to worry about the explanation part. Only point that to mention here is that the tau, the autocorrelation function is a triangular function. Because you people have not studied this digital communication, the example that I'm trying to take is related to digital communication. So don't worry about that. Only thing you need to remember is that you need to understand is that autocorrelation function is a triangular function. Right? Now, autocorrelation, that's what I'm trying to. Now, let's look at the power spectral density. The autocorrelation function is a triangular function. A triangle, a graphical triangle is formed when you convolve a square wave with a square wave. When you convolve a square wave with a square wave, when you do the convolution of a square wave with a square wave, you will get a triangular wave, right? And when you take the Fourier transform of the autocorrelation function, you will get the power spectral density. And when you take the Fourier transform, right? Multiplication of, square wave multiply convolving a square wave with a square wave, right? So that's what I am trying to say here. Square wave with a square wave, when you take the Fourier transform, it will be in the Fourier transform of a square wave will be a sync pulse. Fourier transform of second square wave will be another sync pulse. So two sync pulses are convolving with each other. That means multiplication of Fourier transform of two square waves, right? So multiplication of Fourier transform of two. You take the Fourier transform of first square wave, then second square wave, and then you multiply, because convolution in time domain, and when you do the actually becomes multiplication in the frequency domain, or convolution in frequency domain will become the multiplication in the time domain. But the point is that autocorrelation function is the the power spectral density is the Fourier transform of autocorrelation function. Autocorrelation function is a triangular function here in this case. So how you will get triangular function? You will get triangular function by convolving a square wave with a square wave. And if you look at the frequency domain, it will be the multiplication of the two Fourier transforms of two square waves. And this is how you can plot the power spectral density, average power used as function of frequency. So this is a square by 2. All right. Now in random signals, you can see average usage. So what is the importance of the power spectral density? In random signals, you can see that average usage of frequency domain. Basically, power spectral density, the x-axis will represent the frequency and the y-axis will represent the average power, right? So the frequency, it actually tells the usage of the power with respect to frequency. So that's the purpose of power spectral density. And if T is small, if capital T is small, we will get a more broadened version of the power spectral density curve. So now we know what is the autocorrelation function. We also know what is power spectral density. Let us now try to see the white Gaussian noise. Let us consider noise as a random process. We know that noise can be represented as a Gaussian process. So this is the probability distribution function, probability density function. For noise, mean is 0. So this is a random variable, right? The noise is, a random process where noise is sampled. Now you do what? Do the sampling of the noise, as I did in the case of my previous presentation. We at the receiver, we were doing the sampling, so the noise also gets sampled. So when you get the sampled version of noise, time samples of noise. Each time sample is an outcome of a random variable. Each time sample is an outcome of a random variable. And noise, we know that each noise sample is independent of each other. That means the noise samples are independent of each other. And if we try to calculate the autocorrelation function of noise, it is given by the expected value of noise sample at t, noise value at t plus tau, n star t plus tau. And we know that the noise sample at time t will be independent of noise sample at t plus tau. And if we try to take the expected value, this will be given by a delta function, n naught by 2 into delta function, delta t. This is the autocorrelation function of noise. When we try to find out the autocorrelation, this is from the signals and systems course. When you try to I will put this question in tube sheet to get the autocorrelation function of noise, but I'm using here a direct delta function, right? When the two noise samples are independent of each other, we will get n naught by 2 into delta t. So autocorrelation function is basically a delta function with the height of the delta function as n naught by 2. So autocorrelation of noise at t tau equal to 0, at tau equal to 0, it is n naught, height of delta function, right? Height of delta function. Now the power spectral density is the Fourier transform. So once you try to take the Fourier transform of this autocorrelation function, you will get it equal to n naught by 2. N naught by 2, why n naught by 2? Because positive and negative frequencies. Because n naught, this is n naught by 2. All right. That's why this spectral density is n naught by 2, right? So what I have done is, let me just start from the beginning. I was trying to explain the white Gaussian noise. White Gaussian noise, when the noise is sampled, the noise samples are independent of each other. I am trying to calculate the, noise as a random process. I'm trying to calculate the autocorrelation function nt into n star t plus tau. So two random processes, two noise samples are independent of each other at different times. So when they are independent of each other, the expected value you will get it to be delta t n naught by 2. N naught is some constant value, right? So when you plot the autocorrelation function with respect to time, so at 0 it will be n naught by 2. So that means the autocorrelation function of noise at tau equal to 0. Therefore, n naught is the height of the delta function. N naught by 2 is the height of the delta function. And if you try to take the power spectral density of this autocorrelation function by taking the Fourier transform, it will come out to be n naught by 2 because the Fourier transform of a delta function is 1. It is power spectral density is n naught by 2. And if you try to plot the power spectral density S and F with respect to along x-axis is the frequency, along y-axis is the power spectral density. Since it is n naught by 2, it is constant. You will get a flat curve. Please mute your microphone. So n naught by 2 because we are plotting for negative frequencies and positive frequencies. Anyway, this n naught by 2 is constant. So that's the meaning of white noise. White noise means noise affects all the frequencies in the same fashion. With the same amplitude, the noise affects all the frequencies. That is why it is known as white noise. The spectrum, the power spectral density of white noise is constant. N naught by 2. That's why this is white noise. That's why this is called as white noise. And the variance is given by n naught by 2. So we can find out. I will give you the question in the tube sheet also. Now let us look at what is a Gaussian random process. In general, let us try to define the Gaussian random process. A random process xt is a Gaussian random process if the random variables xt1, random process is xt. xt1, t2 at different times is the random variable. That's what the definition of random process is. The random process xt is a Gaussian random process if the random variable xt1, xt2, xtn are jointly Gaussian. If the random process xt is if the random variables are jointly Gaussian for all choices of t1, t2, and this is the definition of a Gaussian random. There are a number of properties and theorems related to Gaussian random process. Three of the most useful are a random process that is white sense stationary and Gaussian is strict sense stationary, that we can conclude. Integrals of Gaussian random process over a given interval are Gaussian random variables. If you try to take the integral of a Gaussian random process over a given interval, so you will get basically the Gaussian random variables. And random variables over many different intervals are jointly Gaussian random variables. The process defined by the integral of a Gaussian random process over minus infinity to t as t varies from minus infinity to plus infinity is a Gaussian process. So if you try to take the integral of a Gaussian random process, result into yt, which will again be a Gaussian random process. What is a Gaussian random process? If the random variable xt1, xt2, xtn are jointly Gaussian for all choices of t1, t2, tn for all. I will not derive the formulas here. This is the first order probability density function for Gaussian random process. If a Gaussian random process is characterized by its mean, autocorrelation function is this. Its first and second order density functions can be written in the form of mean and autocovariance function. So we can write the, we can derive these things also. I will see whether to put this question in the tube sheet or not, but this is the first order density function and this is the second order density function for the Gaussian process. So this is given 1 over 2 pi under root of mod k exponent and all the variables, all the values are defined here. This is the second order density function for Gaussian random process. Now, what is white random process? I have already discussed. Rather, the power spectral density is n naught by 2. For K, it is convenient to define the white noise process. The name comes from the fact that the spectral density is assumed to be flat and contain all frequencies. That's what I have just explained to you. The same thing, n0 by 2, the autocorrelation function, we have already calculated it. I will put the question in the tute sheet also, right? So white noise autocorrelation function, white noise PSD function, we have already just now calculated. So in this lecture, we have discussed with what is Gaussian distribution. Because I am trying to explain you the 5th chapter, which basically deals with the modeling of noise, right? In that, I started with the Gaussian distribution. Then, as per the central limit theorem, I explained that how from different random variables, a Gaussian distribution is can be the result. And then I try to explain you what is autocorrelation function, what is power spectral density of noise. We calculated also. And then we have just defined what is a Gaussian random process. All right. Okay. So that's the kind of stuff which is present in chapter number 5. We will go more into this chapter and we will try to solve some questions also. And I will give you the questions in the tute sheet also. That's basically the modeling of noise. Noise is, we are talking about the AWGN noise in the receiver electronics or any electronic circuit for that matter. So I will end my lecture here. If any questions are there, you're most welcome to answer. You're most welcome to question. And I'll be happy to answer it. Otherwise, I will end the lecture and we'll meet next time. Syllabus I have already told you for the second evaluation. It is chapter number 2 and chapter number 5 of the syllabus, which are basically chapter number 2 deals with random processes, which we have just covered previous to this day. And now we have started with chapter number 5 also, which we are covering. So syllabus is chapter number 2 and chapter number 5 of the syllabus. Chapter number 3 and chapter number 4 will be for your next, when you will come offline here. And that will, from that syllabus, the written examination will also be shared. All right. Thank you very much for joining.